Alright guys, here we are back at 7.3. Had to split this up into two parts because it was just a little bit too much for one lesson. So for the second half here, we're going to get into fractional exponents in which we don't have 1 in the denominator anymore. Okay, so they use m and n, I don't know why they make this so confusing, but shouldn't be that bad. So look, all this is saying, and it's helpful to think about this in two ways. So I'll give you the book's definition, and then I'll show you what it means with an actual example. So what this is saying is if we have any number, any real number b, any positive real number b, okay, so you could choose any positive number. We could choose a 3 if we wanted to. And any integers m and n bigger than 1. So the m and the n relationship is this. So I could say, like 3/4 or something like this. Okay? Then b to the m over n, which I'll show you what this looks like with this 3 in just a second, can be written it can be written in two ways. It can be written as the mth root of b to the n power, or you can also write this as the nth root of b and the whole thing is taken to the mth power. It's helpful to actually, and did I do this right? Sorry, this should be an n, this should be an m. I apologize, you guys. Make sure that's right in your notes. That's very important. So look, let me just point something out. The denominator here always is the root that we're taking. The numerator, I'll do this in green, is always the power that is being applied to the base. Okay? So if it's something other than 1, see if it's 1, what the nice thing about 1 is anything to the first power just keeps itself, right? So, when we were doing something like 3 to the 1/2, right? If we did like 3 to the 1/2, that was saying the same thing as the second root of 3 to the first power. But by default, the square root sign just means second root, so we don't put that. And then anything to the first power we don't worry about, so we didn't put that. So we just said that 3 to the half is, the square root of 3. The same rules apply, same rule hold up. We just don't write in that little 2 and that 1 because it doesn't change anything. Okay, so maybe we should, just to get used to that habit. But that's okay. So here for this, if I have 3 to the 3/4, what that means is I'm taking the fourth root of 3 to the third power, or we said we could also write this as the fourth root of 3 all taken to the third power. And again, sometimes it's convenient to do it this way, other times it's convenient to do it this way, but ultimately if you evaluate both of those, you'll get the same answer. So it's just another way of thinking about it. Then they give this example 8 to the 2/3. 8 to the 2/3, that's the same thing as 8 squared, and then taking the third root, okay, because the denominator is 3. So this is the third root of 8 squared. So that's the same thing as the third root of 64, which we know is 4. Another way to think about this is I could have done the third root of 8, right? Evaluate that first if that's convenient, and then square it. We know the third root of 8 is 2. 2 squared is 4, right? So that's just another way to think about it, which could come in handy and will come in handy here for example 4. So for 4a, we have 27 to the 2/3. Okay, so we could say that that's the same thing as 27, the third root of that 27, right? All squared. The third root of 27 is pretty simple to find, right? Because that's the same thing as 3 times 3 times 3. Therefore, the third root of 27 must be 3, because 3 to the third power is 27. So I can evaluate that first, and then take that and then square it. If I do that, I get 9. Okay, the other way to do this is you could have actually, found the third power of 27. You could have squared the 27, found that big number out, and then taken the third root of that. You should also get 9. Either way is okay. Okay, but you'll especially want to do it the first way, the primary way for this one. This one's a big number. So let's just look at this one here. So this is like saying we'll take the fourth root of 256. Now, if you took this to the fifth power, that's like 1 trillion. It's like over 1 trillion. So let's not do that. Let's take the fourth root of 256, and then whatever that answer is, take that to the fifth power. And we'll end up with the same answer, but we'll save ourselves from some big numbers. Okay, so the fourth root of 256, let's find out what multiplies by itself 4 times and gives me 256. Well, I know that 2 is not big enough, right? So if I did 2 times 2 times 2 times 2, that's only going to give me, what, 16? And then 3 is only going to give me 81. So let's try 4. 4 times 4 times 4 times 4, that gives me 16 times 16, which is equal to 256. So that one works. So the fourth root of 256 is 4. And then I could take that 4 to the fifth power. Okay, so 4 to the fifth power, well, I already know 4 to the fourth. I can just multiply this one by 1 more 4. Or I can do this in my calculator where you take 4. Usually there's a little caret sign someplace on your calculator. That's how you would raise something to a power. So you could hit that little button and then hit the 5. And you should get, when you do that, 1024. Okay, when you multiply that out, you get 1024. Couple ways to find that. Okay, so that would be the answer to 4b. Now, let's look at example 5, but before we do, let's think about this power property of equality. Okay, so once you have, essentially what this power property tells us is if you have the bases the same on both sides of an equation, you can set the exponents to equal each other. Okay, so what that looks like is, say for instance I have, let's see, what could an easy one be? What if I had something like 5 to the x is equal to 5 to the third? That's an example that's in the book. What this is saying is if this base is the same, once these bases are the same, you can forget about them and just set this exponent to equal this. Because, so in this case, it would be just x equals 3. Because, if you plug that back in, 5 to the third does equal 5 to the third, right? So we want the bases to be the same. That's really the goal, is to get to the bases to be the same. So we'll do some of those here in just a second. In fact, I don't know why they skipped this, but let's put these in here. This is example 5, and if you don't have this in your notes, perhaps you write this into your notes for example 5. This is an important thing that you'll be doing in the homework. So example 5a says we have 5 to the x is equal to 125. Okay, so is there a way that I can write, so I can't really simplify this 5 down any further, right? So, but this 125, can I make that look like that 5? In other words, can I take 5 to some power and make it equal to 125, right? So I want to write this as a base 5. Okay, so let's think about that. If I have 5 times 5, that's 25, times 5, 25 times 5 does equal 125. So that means 5 to the, there's 1, 2, 3 of these 5 to the third power is equal to 125. So since that is the case, I can do this. I could drop my bases and say that x is equal to 3. Okay, let's do one more. This is 5b, which I prefer you have in your notes as well. For 5b, we'll do it in red here. For 5b, the example is 12 to the 2x plus 3 is equal to 144. So again, I'm trying to get my bases to be the same. This one's the smaller one. Let's try to get this one to be 12. So can I write this as as a base 12 to some power? And yes, you can. That's hopefully you recognize this actually, that this is 12 to the second power. If you didn't know that though, you could just start running through. You could do 12 times 12, and then you'd see right away that that's 144, so it'd be 12 squared. So I have 12 squared equal to 12 to the 2x plus 3. Once the bases are the same, you guys, okay, once these guys are the same, we can forget about them now using our rule, power property of equality, and I can just set these guys to equal each other. So 2x plus 3 is equal to 2. Subtract 3 from both sides. Just doing some simple algebra now, I get 2x is equal to negative 1. Divide both sides by 2, and I get x is equal to negative 1/2. Okay, so for 5b, if I plug a negative 1/2 in there, that'll make this go to 2. 12 squared is equal to 144. Okay, so that's using your power property, which we'll probably have to play with that a little bit more in class, but that's okay. At least get used to it right for now. Final thing for today is the word problems here. Just taking these exponentials and putting them into practice. It says the radius r of the nucleus of an atom of mass number A is r equals 1.2 times that A to the 1/3 femtometers. So find A if r is equal to 3.6. Okay, so what I'm going to do is I'm just going to plug that 3.6 in for r. So I get 3.6 is equal to 1.2 A to the 1/3, and we're trying to find this A. Trying to get this thing all by itself. So to do that, I'm going to divide both sides by 1.2 first. Okay, when I do that, 3.6 divided by 1.2, I believe, is just 3. So that's 3 is equal to A to the 1/3. Now it's asking me basically to take the, so if I wanted to get A by itself here, I could multiply this by, or take this to the 3rd power, right? If I have a 3rd, and I take it to the 3rd power, these cancel and I'm left with A. But if I do that to one side, I also have to take the 3rd power of the other side. Therefore, A is equal to 3 to the 3rd, or 27. 3 to the 3rd power is 27. Okay, so there's how we solve for that atomic mass number. This is something that you're going to see in chemistry here in the next couple of years. Okay, that's it for now, you guys. For the homework, don't worry about this for now. I have a homework sheet for you, and we'll catch you guys in class where I'm sure we will be working a couple of these together.